Group 1 would now like to present detection of algae in fish tanks using optical absorption.
Our main motivations for this project are to create a design that is both affordable and effective at detecting the presence of algae in water, because the presence of algae in water in large quantities can mean that there are too many nutrients present. Our basic goals are to design and build a system that uses the difference in input and output light intensity to get the percentage of transmitted light, to design and code a user-friendly touchscreen display, and to keep our budget under $1,000. Advanced goals: design and build a siphon system so that the fish tank can be continuously checked. Integrate a thermal camera to check water temperature and make it Wi-Fi compatible. Our stretch goals are to make an app to go with it. Design a system to dispense corrective chemicals. Project description: microcontroller used to power, read, and display outputs. Laser, lenses, and photodiodes used to detect intensity shifts. Thermal camera used to monitor temperature. Liquid crystal display and Wi-Fi module used to communicate with user. Siphon used to draw continuous water sample. Here is a graph of our specifications for our algae detecting system. We have it broken down into separate components. Each component has its own parameters and design specifications. This block diagram shows the distribution of work being done, using different colors to represent each person. Danielle is blue, Keelan is yellow, I am orange, and Virgin is green.
Thank you, Zia. I'll be taking you through the electrical hardware components for our system. As you saw on the previous page, our system has a few accessories. These include items such as a laser, and photodiodes for the optics system, as well as a liquid crystal display for the user interface. Based off our design, some components will require an analog pin, while others will require a digital connection. Through our research, we determined that the Arduino Uno would be the best microcontroller for our design. The board has a 5 and 3.3 volt pin that can easily be coded using C++ via the Arduino Integrated Development Environment. The microcontroller not only meets our component integration requirements, it also has an extensive online community with countless project examples. Here you can see the schematic of the Arduino Uno. The power supply is at the top, followed by the USB bridge below on the left, and the Atmega 328 microcontroller on the bottom right. Next, we have the power supply for our system. Our design requires continuous power, so a wall adapter was selected as opposed to batteries. Based off the Arduino Uno specifications, we needed input voltage between 7 and 12 volts. We chose the FlickerStar power cable due to its input voltage range and inexpensive cost. The Arduino Uno will receive power through a 6-foot 5.5 mm by 2.1 mm DC barrel plug. Next is our display. First, we had to determine which type of display would be best for our design. After our research, we found that a liquid crystal display would be beneficial for its touch-enabled feature and low cost. Specifically, we chose the Resistive Touch 2.4-inch Nextion liquid crystal display shown here. Nextion has a very similar business model to Arduino in that they both have their own editors with extensive training material to support new users. Virginie and I will have the task of programming the display and then using those variables from that code in the main Arduino code. Last, we have the Wi-Fi module. This is going to allow our user to access the device remotely via the internet. The ESP8266 and ESP32 are the most popular ESP modules, with the ESP8285 being a continuation of the ESP8266. Our system is simple and does not require a Bluetooth connection, and based off cost and basic functionality, the Maker Focus ESP8266 was our top choice. Here you can see the schematic for the Maker Focus ESP8266. And that completes the electrical hardware for our design. Next, Keelan is going to walk you through the optical hardware.
Here you can see the specifications for the optical components. For our light source, we have the following: a collimated beam, wavelengths of 450, 532, and 650 nanometers, where the green 532 and the red 650 nanometer wavelengths are common operating wavelengths and will be used for sensitivity calibrations, and the optical power is no greater than 5 milliwatts. Next, we see the beam splitter specifications: a visible light anti-reflective coating to minimize unwanted reflection, a 50-50 power split ratio for the split beams to have identical optical power, and a 25.4 mm diameter for easy alignment purposes. The specifications for the focusing lens include the same anti-reflective coating as the beam splitter, a focal length no less than 25.4 mm but no greater than 40 mm to ensure there is enough room between components but not too much where beam distortion may occur, a 25.4 mm diameter for easy alignment purposes, and focuses diverging light for refocusing the beam due to any divergence caused by transmitting through water. The last optical component is the photodiodes, where the specifications include an active area no less than 4 mm squared so the alignment remains simple, a sensitivity and/or responsivity of no less than 0.5 at 450 nanometers, and lastly, they are no more than $10 each. Next, I'll go through some optical component comparisons. The Alpac laser pointer displayed on the left-hand picture was chosen for matching one of the specified wavelengths of 450 nanometers, which is the wavelength chlorophyll A absorbs the most. The power source is a simple pair of AAA batteries, which makes powering it from a circuit easy. And lastly, the max power is 5 milliwatts. In comparison to the big laser pointer brand, with a maximum optical power of 2,000 milliwatts, costing around $20 more and requiring 2 lithium-ion batteries, the Alpac laser pointer was an obvious choice. Next, we see the laser pointers from the Amazon store displayed above on the right side. These lasers come in a set of 3, operating at 405 nanometers, 532 nanometers, and 650 nanometers, and all have a maximum optical power of 5 milliwatts. These laser pointers were purchased for preliminary testing but have since been used for wavelength-dependent sensitivity calibrations. Here we look at the comparison of beam splitters. Beam splitter 1 seems to meet all of the specifications, including a 25.4 mm diameter, a 50-50 split ratio, and a visible light anti-reflective coating. In comparison to beam splitter 2, which is a cube beam splitter and meets all of the specifications, however, it is more than double the cost of beam splitter 1. Next, we see beam splitter 3, which doesn't really have a given split ratio, doesn't have an anti-reflective coating, and doesn't meet the size specification either. Lastly, we see beam splitter 4, which is a square plate beam splitter and meets the split ratio and anti-reflective coating specifications, but is over the size specification and is more expensive than beam splitter 1. From this comparison, beam splitter 1 was the obvious choice for our project. Here we look at lens comparisons. The only differences between these lenses are their price and focal lengths. As for the comparison, lens 1 with a focal length of 25.4 mm is at the lower limit specification for the focal length. It is also the most expensive out of the 3. Lens 2's focal length is in the middle of the focal length specification at 30 mm, allowing enough room for mounting. Lens 3's focal length of 40 mm is at the upper limit of the specification, but is the least expensive out of the 3. However, the longer focal length increases the chances of beam distortion. All of these lenses are able to focus diverging light due to their biconvex shape. However, we decided to choose lens 2 for the project due to the focal length being just right, not too short and not too long. Lastly, I'll go over the optical design. We start with a laser pointer of 450 nanometers propagating a beam of 2.4 milliwatts of average optical power, 5 centimeters to the beam splitter, where it's split into 2 separate beams of roughly 1.2 milliwatts each. The input beam path is a transmitted path where the beam transmits to the beam splitter and travels 3.4 centimeters to photodiode 1 for the input intensity to be detected. The output beam is the reflected beam from the beam splitter that travels 4.4 centimeters to the first surface of the water tube. The beam then exits the water tube and travels 2.4 centimeters to the focusing lens. The lens focuses the beam 3 centimeters away onto the photodiode 2 for the output intensity to be detected. By detecting the input and output intensities, we can find out how much of the light was absorbed by dividing the output intensity by the input intensity. Next, Zia will explain the optical system testing.
We are going to test the optical system by comparing the calculated value for absorption using Beer's law and then compare that to the collected data. The theoretical values for absorption and transmission are all shown on the left side of the slide. To the right are the diagrams of our optical setup. The hardware components consist of the 3D printed parts that we designed in FreeCAD and the water tube that we have constructed for our water sample.
In this part, we will concentrate on the software design and components, and we will talk mainly about the microcontroller coding and interface as well as the LCD interface. We had three different goals for the software component of this project. The first one was the main goal that we wanted to achieve no matter what, and that is program the microcontroller sensors and buttons to make sure that the actual product is functional. The advanced goal that we had for this section is have the machine operate through a touch LCD screen and make a user interface through there. Finally, our stretch goal is, and that is when we have enough time to achieve it, is that we would build an app to control the product through a smart device and make it as user-friendly as possible, as well as send notifications to the users. In doing so, we had to have a breakdown diagram of how we're gonna proceed and how the software process will proceed. We divided the software process into three different categories. We needed to make sure that the device would power on and off, as well as we would be able to control it through the LCD, and then we would worry about the testing part. Like I said, the power aspect of it all, it needs to make sure that the coding would turn on and off the machine, and then we can control it later on through the LCD controller, which means it needs to read the sensors, turning off the system and turning on the system, the I/O, which would be the Nexion touchscreen and the app as a stretch goal, and then we would have the code comply and work with all the different types of machines that we have working and all the connections. Also, for it to send notification to the user if possible, and have it as user preference and configuration set for that. Slide, we will take you through the coding planning process and our pursuit of code to program our device. In order to start out the coding process, we looked at previous examples of skeleton codes in order to build the foundation of the program that needs to run on a microchip. Then we downloaded the software of Nexion, which is what the LCD display uses to program it, and we used the libraries and skeleton code to connect Nexion display with our microchip using the IAD on both Nexion and Arduino. Next, we were able to start coding the LCD display after we made out the first draft of the LCD interface on Nexion, containing the buttons and pages needed for the user to be able to use the device. Then we programmed our photodiodes and thermal camera using the Arduino IDE so they can detect the readings needed for the device. After that, we were able to add the laser code to turn them on and off on command. Finally, we updated the Nexion LCD display with our new design and buttons to reflect the changes in the skeleton code. This was our favorite part, as we get to witness all the components working through the interface we created for the user to be able to control the device. We started with a draft for the design that was very minimal to test out the buttons with the microchip and see if they are functional, but as we approached the end of the project, we were able to change the design slightly while maintaining the functionality of the buttons on the LCD system. This part was mainly done on the Nexion software working hand in hand with the Arduino IDE that programmed the function of each button on the LCD screen. So to recap on our software design goals and what we were able to achieve in this period of time, we were able to successfully achieve our main goal and advanced goal. However, due to time constraint, we were able to make the device Wi-Fi ready, but not able to achieve the stretch goal of making an app. However, in the future, if more work is done on the system, an app can potentially be linked to the device through adding the Wi-Fi code we have already made accessible.
Administrative information. In this slide, as you can see, we have made two tables to express the budget and financing. The first table shows the budget cost and the actual cost of each system component that we have. And we have successfully stayed within the expected margins. On the second table, however, you can see that we have the financing categories that we have used in order to pay for those components. We have three categories in that table: the total personal contribution, the total awards, and the final personal contribution. For the work distribution, Danielle was in charge of the system design, which is including PCB design, hardware ordering, component testing, and system troubleshooting. For the optical design and system housing, Keelan and Zia worked together on the optical design, optics and hardware ordering, budget and financing, 3D print designs, and Zia assisted with the optical design as well, the housing design, custom water tube design, and 3D printing. For the system software, Virgin, assisted with the coding, component calibration, user interface on the LCD, and user interface through a notification app. We had few design issues, and we are working on finding some of the solutions, as well as we already found some solutions for some of the problems. In the case of the optical design issues, the water tube optical path length of 6 mm, not long enough for sensitive allergy detection. Also, as chosen photodiodes are not sensitive to red light. The solution for that was to design custom square water tube with internal optical path length of roughly 25.4 mm and borrow second set of photodiodes from the undergraduate optical lab. For the hardware design, we are facing the issue of laser pointers overheats and loses optical power after 3 minutes of continuous operation. For the software design issue, we have some compiling errors and must align the components to work correctly with the hardware components, as well as we're looking into some missing libraries that we want to add into the coding. We had few design issues, and we are working on finding some of the solutions, as well as we already found some solutions for some of the problems. In the case of the optical design issues, the water tube optical path length of 6 mm, not long enough for sensitive allergy detection. Also, as chosen photodiodes are not sensitive to red light. The solution for that was to design custom square water tube with internal optical path length of roughly 25.4 mm and borrow second set of photodiodes from the undergraduate optical lab. For the hardware design, we are facing the issue of laser pointers overheats and loses optical power after 3 minutes of continuous operation. For the software design issue, we have some compiling errors and must align the components to work correctly with the hardware components, as well as we're looking into some missing libraries that we want to add into the coding. For our project progress update, electrical components have been isolated and tested, PCB has been designed and soldered for voltage regulation, graffiti siphon has been designed and constructed, initial system testing has been completed, software design and code has been completed and successfully compiled and printed the correct values for test photodiode, control photodiode, and the light absorption, as well as turning the laser on and updating the values constantly. The LCD is having issues reading multiple values for the Arduino. Thermal camera requires too much dynamic memory. After taking you on a journey of the the designing and the building process of this device, we conclude with confirming that we were able to successfully build this device and make it operational and functional for the user. All the parts necessary to create this device did exist, and using our research, design and building process as well as implementation methods, we were able to make it functional for the user to be able to test algae in the water. This concludes our presentation, and we would love to hear some questions. Thank you.